This is the intro chart for drag. Drag is the force experienced by a body if you drop it, and it opposes the downward velocity that it has as a result of the acceleration of gravity. This is the expression for drag. It's v hat is a unit vector in the direction of the velocity, and so the negative sign here means it's anti-parallel to the velocity. And before talking about the factors, there are some caveats to being able to apply this expression for drag, um, which incidentally is proportional to the velocity squared. So this drag formula applies if you're first of all close to the Earth, and that's true because as you go further up, the well, first of all, the acceleration of gravity would change, but the density of the air would also change, and so the drag coefficient would start being a function of the altitude, which clearly isn't modeled here. And the size of the particles being modeled would have to be between roughly several millimeters to several meters in size. Your book says a few millimeters to a few meters. So this is about right. Really small particles wouldn't work. Really big ones wouldn't work either. And the third caveat is that V can't be too large. It has to be less than a couple of hundred meters per second or less, because then you start, for larger values of velocity, you start getting some nonlinear effects. So with those caveats, we can apply this equation, and it is an approximation, and so keep that in mind. The C depends upon the shape and the orientation, and it's dimensionless. You should be able to check this equation and tell me why C is dimensionless. Rho is the mass density of the air in kilograms per cubic meter. And somewhat surprisingly, 1 cubic meter of the air contains 1.2 kilograms of air at standard temperature and pressure. Um, and A is the cross-sectional area in square meters. Um, so, um, it's not a good model for dust particles, well, because they're too small, bullets because they're too fast, and in liquids like water, um, because it uh, behaves differently, quite a bit differently from the way the physics is somewhat different. And so your book gives you three C uh, factors, one for a sphere, 0.5, one for a cylinder. If it's downward facing, 0.8, one for a cylinder. If it's sideways facing, 1.1. And so they do an example here in your book for a car, and so they take a car that has a mass of 1,500 kgs, and it has approximately a rectangular cross-sectional area if it's going forward, width of about 1.6 meters and a height of 1.4 meters, which gives an A of 2.24, and the C is 0.35 for what we'll assume for this car, and that's partly because aside from this cross-sectional area, there is some aerodynamic engineering that's done in the car, and so the C is somewhat smaller. As you can see from the formula, a smaller C makes a smaller drag. So that would be, of course, desirable in a car. You're going to eat up um, gas overcoming a drag force, and so it behooves an engineer to make the C as small as reasonably possible. Okay, so the question is, at what speed, at what speed v will the drag force be equal to the car's weight? and let's assume that the engine is off. So in other words, it's coasting at some velocity, at some speed, some forward velocity. And so in that case, the free body diagram would look something like this. There would be a gravitational force downward, normal force of the road upward, and then a drag force acting opposing the motion, supposing, of course, that the motion is anti-parallel to D, as shown here. And so we are assuming that the magnitude of the drag force is equal to the weight of the car, and so we can solve for V. And if we do, we would get square root of 2mg times c times rho times a. So plugging the numbers in, 2 times 1500 kgs, 9.8 meters per second, 0.35 for the c factor, 1.2 kilograms per cubic meter for the air, mass density, 2.24 meters squared for the cross-sectional area. That gives us 180 meters per second, and if we convert that to miles per hour, that's pretty fast, 400 miles an hour. That's faster than any normal car would go. All right, so a couple questions you might be interested in doing. First of all, can you find the time for the car to slow down from 180 meters per second, which is what it would be going at here, to 50 meters per second? Okay, now the tricky thing about this, of course, is that the force is no longer constant, which means the acceleration is not constant. So you can't use the equations, constant acceleration kinematic equations, when you have to use calculus. And the second one is to find the displacement of the car during the slowdown. And the hint there is that you can re-express dv dt via the chain rule as dv dx times dx dt, and dx dt is v. So stop the YouTube and see if you can figure those two things out. The next segment, I'll show you how to do that. All right, so here was my solution for the first one. So AX is equal to dv dt, which is equal to minus 1 over 2 MC rho AB squared. So you can set the integral up as I show here. And basically after integrating, you'd be integrating v to the minus 2. The integral of v to the minus 2 is minus v to the minus 1 between the starting and ending speed. The integral on the right-hand side is trivial because this is a constant, so it's basically just this constant times t. So we can now take this and we can solve this for t. T is equal to the difference in the reciprocal speeds times 2m times c rho times a. So if you plug the numbers in here, 2 times 1500 kgs divided by 0.35, c, 1.2 kilograms per cubic meter, rho times a, 2.24 square meters, that's the cross-sectional area, times the reciprocal of the ending velocity minus the reciprocal of the beginning velocity. It takes 46 seconds to slow down. That's quite a long time. When you do things like this, you should definitely go back and check your units. And so this whole thing should be in seconds. And so kilograms, meters to the minus 3, meters squared, times 1 over meters, seconds to the minus 1. This is reciprocal speed. Well, so the kilograms cancel, and if you look in the denominator, the meters cancel, and they get seconds to the minus 1 in the denominator, which means it's seconds in the numerator, consistent with the time dimensions that I'm expecting. Okay, part 2 of this was to figure out what the accompanying displacement was, and so we'll use the hint a sub x is equal to dv dx times v, which is equal to this, and so now I can divide through by v, and I'll lose one of the powers of v, so I get dv dx is equal to something that's proportional to v. Now when I divide by v, I have an integral of dv over v, which is going to give me a ln from v0 to v1, and a integral for the x direction, which is trivial because this is constant. And so the integral on the left is ln vy over v0, and on the right it's I'm integrating from 0 to delta x, so it's minus c rho a over 2m times the displacement I'm trying to find. And now I can now solve this for displacement. Displacement is minus 2m over c rho a times ln of v1 over v0. So plugging the numbers in, minus 2 times 1500 kgs divided by 0.35 times 1.2 kilograms per cubic meter times 2.24 square meters, ln of the ratio of 50 to 180 meters per second, and that gives 4080 meters. That's a little over 4 kilometers. Again, let's check the units here. So if you check the units, you'll see kilograms cancel as before. This is dimensionless, and so basically I just get 1 over m to the minus 1, which is m as appropriate.